Welcome to the Explainer. Have you ever flipped over a bottle of shampoo or, looked at the ingredients list on a packaged snack and just found yourself staring at a terrifyingly long, unpronounceable chemical name? Words with numbers, commas, and dashes sprinkled in like some kind of secret code? It literally feels like trying to read a foreign language. And frankly, to most people, that's exactly what it is. So, what does this all mean? How do chemists actually name these complex molecules? Well, today I want to completely reframe how you think about chemistry. It's not just some dry, boring list of rules you have to memorize. No way. It's actually a highly logical, deeply elegant language of science just waiting to be learned. And honestly, just like any spoken language, once you understand the alphabet and the underlying grammar, you can decipher and read pretty much anything. The key to decoding this whole universe is IUPAC nomenclature. Now, IUPAC stands for the International Union of Pure and Applied Chemistry. Decades ago, they realized something absolutely crucial. If scientists across the globe were ever going to collaborate, share research, or, say, discover new medicines, they desperately needed a systematic method to name organic chemical compounds. IUPAC nomenclature is basically the universal grammar of chemistry. It transforms what looks like pure rote memorization into a perfectly structured, totally decipherable system of global communication. So here is our roadmap for today. First, we'll cover the vocabulary of chemistry. Second, the rules of numbering. Third, dealing with complex branches. Fourth, the functional group hierarchy. And finally, decoding common chemical names. Don't worry if this sounds like a dense rulebook. I promise it's highly navigable, and we're going to build it from basic vocabulary all the way up to complex sentences. All right, let's jump straight into Section 1, the vocabulary of chemistry. We're going to learn the functional group building blocks. Okay, let's dive into this. You see, every language needs words, right? And in organic chemistry, our foundational words are built using specific arrangements of atoms, which we call functional groups. Notice how these specific atomic arrangements dictate the suffix, the ending of our chemical name. For instance, if a molecule has an OH group, it belongs to the alcohols, and its name ends in -ol, like butan-2-ol. A carbon double bonded to an oxygen? Well, that's a ketone, ending in -wone. Carboxylic acids end in oic acid, and amines simply end in amine. By just spotting these groups, you immediately know the family the molecule belongs to. It's essentially how our chemical words are born. Moving right along to Section 2, the rules of numbering. This is the syntax of our molecular chains. So let's see how this builds into the actual syntax of our molecular sentences. We know the words now, but how do chemists decide exactly where to start counting on a really long carbon chain to place those words? Well, this brings us to a fundamental law, the lowest sum of locants. When a carbon chain has branches or attachments, we have to number the carbons to say exactly where those attachments live. The absolutely crucial point here is that correct grammatical syntax in chemistry demands these attachments sit at the lowest possible numbered positions. Think of it like this. If you number the chain from one end and get a certain set of numbers, and numbering from the other end gives you a higher set, the lower sum always wins. Take a look at the specific molecular structure of 4-ethyl-3-methylheptane to really see this mathematical rule in action. The longest chain is 7 carbons long, which gives us our root word, heptane. Now we have 2 branch attachments here, an ethyl group and a methyl group. If we number the chain from right to left, the attachments fall on carbon 3 and carbon 4. 3 plus 4 equals a sum of 7, right? But if we were to number from left to right, they'd fall on carbons 4 and 5, which sums to 9. Because 7 is obviously less than 9, the right-to-left numbering is the only grammatically correct way to write it. It's an incredibly simple but really beautiful mathematical elegance. Let's turn to Section 3, dealing with complex branches. We're talking about navigating double bonds, triple bonds, and halogens. Now that we've got the basics down, we're ready for slightly more complex clauses in our chemical language. I mean, what do we do when our molecule is an unsaturated hydrocarbon, meaning it actually contains double or triple bonds? The logic here remains super rigid, operating in a strict step-by-step fashion. Step 1. You absolutely must find the longest chain that actually contains those multiple bonds, even if a longer continuous carbon chain exists somewhere else in the molecule without them. Step 2. You number from the end nearest to that multiple bond, giving it priority over the simple carbon branches. And Step 3. When writing the final name out, you alphabetize the substituents. The multiple bonds literally dictate the flow of the entire molecule. Let's look at the specific molecule oct-2-N-5-ine, and this brilliantly illustrates a very specific, kind of fun quirk in the IUPAC rulebook.
What happens when you have both a double bond, an ene, and a triple bond, an yne, in the exact same compound? Well, when numbering, the double bond gets the priority for the lower number. That's exactly why we number from left to right here, giving the double bond the 2 position and the triple bond the 5 position. So it's oct 2n 5-yne, not oct 3n 6-yne. The rules are absolute for sure, and they completely prevent any confusion.
Next up is Section 4, the functional group hierarchy. This is all about polyfunctional compounds and the battle for priority. We're really building to the climax of our molecular narrative now, because what happens when 2 different functional groups are in the exact same molecule, and they have to fight for dominance, like who gets to define the molecule's ending and who gets demoted? Well, the IUPAC system uses a strict hierarchy. Think of it essentially as a trump card system to establish the principal functional group. Carboxylic acid is at the absolute top of the food chain. It outranks almost everything. Below that, we've got sulfonic acids, esters, acyl halides, amines, and then aldehydes and ketones. Down near the bottom are your alcohols and amines. The winner of this molecular battle gets to be the grand suffix at the very end of the word, while the losers are relegated to subordinate prefixes at the front of the name. Consider the structure of 6-hydroxyhexane 2,1. This perfectly captures that exact battle for priority. This single molecule contains both an OH group, an alcohol, and a C double bond O, which is a ketone. If we recall our hierarchy from a second ago, the ketone outranks the alcohol. Therefore, the ketone claims the suffix, giving us the root name hexane 2,1. The alcohol is completely stripped of its all ending. It's demoted to act as a mere prefix, becoming hydroxy, living all the way over on the 6th carbon. It's a pretty ruthless structural hierarchy, but man, it completely removes any ambiguity for scientists. Finally, we reach Section 5, decoding common chemical names. Let's look at the slang and idioms of chemistry. We've spent our entire time today focused on the rigid, beautiful logic of IUPAC syntax. But out in the real world, chemistry is full of messy, historical slang. Now, what's really interesting about these older, common names is looking at deeply historical and often incredibly dangerous chemicals like mustard gas, phosgene, and tear gas. These are names given by the very people who first synthesized them, or they're based entirely on how they smell, or maybe what terrible things they do on a battlefield. They're basically scientific idioms. They tell a fascinating story about human history, but honestly, they tell you absolutely nothing about the molecular structure itself. When we contrast the 2 systems side by side, the absolute necessity of IUPAC becomes crystal clear. The common names are historical, highly unpredictable, and frankly, scientifically trivial. I mean, imagine trying to build a global scientific enterprise where a researcher in Japan calls a chemical by its smell and a researcher in Brazil calls it by the color of the rock it was found under. It would be total chaos. The IUPAC system, though, is unambiguous, highly structured, and universal. Looking at those terrifying, vague historical names perfectly demonstrates exactly why the global scientific community desperately needed a strict, unifying rulebook. We have covered a tremendous amount of ground today, transitioning from the total chaos of arbitrary names to the absolute clarity of molecular syntax. So I want to leave you with this provocative thought. If you discovered a brand new molecule today in a lab, how would you construct its name using this universal grammar? Think about it. You now possess the linguistic key to decode the chemical universe around you. Next time you look at the back of that shampoo bottle or an ingredients list, don't be intimidated by the dashes and the numbers. Look for the prefix, spot the suffix, follow the numbers, and read the language of the molecules. Thanks so much for joining me on this explainer.